moles. And then, what are you going to start with us in this problem, Matt? This math.
I took the 9.46 grams.
Okay.
And wanted to get 2 moles of lithium bromide, so I divided by the into moles by taking 1 mole divided by molar mass.
211.9 grams
right.
per 1 mole. Got it. And then what did you do to follow up? Other math?
I put that into the molarity solution.
So you got moles first. You stopped and calculated moles.
Yeah.
Brandon, what did you get for moles? 0.045 moles. Thumbs up. Everybody else got that? Okay. So when he says he put it into the molarity expression, what does he mean by that, Peyton? So liters, good. So this needs to be in liters. So that's just remembering that your molarity units are moles per liters. Moles of solute over liters of solution. Avery, what did you get as your final? 0.1784 molar, so big M. And then how many sig figs should that be rounded to? 3 sig figs, so that should be rounded to 0.178. Good. So 0.178, oops. There's space. 0.178 molar. Good. And that's approximately, that's a really dilute solution. We're going to be making different concentrations of solutions today. All right. Allie, how do you start the next one?
Well, you have to find out moles on moles of X, and then
So 0.25 liters being 250 milliliters in liter form. Okay. Okay. So I'm okay with you guys setting up these as proportions like this, but you can't always, if you're given a molarity and a volume, you can multiply them by each other to get moles, right? M times V gives you moles. Remember writing that down in your notes? So you can do that, and that's exactly what we're going to do here, so for X, right? So we're going to do molarity times volume, or volume times molarity, whichever way, to give you X. So what is X? Okay, so don't need to round yet because we're not even to our final answer. So how many moles of sodium chloride are in blah, 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 blah. How many grams is that? Okay, so this is one of our final answers. How many sig figs should this be rounded to? 2 because of the 4.9, so that should be 1.2 moles. And then, Maddie, pick up. How do you get to grams?
you find the molar mass of sodium chloride.
Okay, so 1 mole of sodium chloride weighs 58.45. My board's a little off now again. Okay, and what is that in terms of grams, James? 70.14. And that's grams. Okay, and that should be the 70 grams in terms of sig figs. All right, so not bad, right? We know molarity pretty well. What's molality? Moles over kilograms of what? Solvent, not solution. So that's gonna be different. But I'm actually not gonna worry about that right now. We'll hit up molality again tomorrow when we talk about related properties. Last thing we're talking about before we get to that is dilution. And the dilution equation is one that you may have seen in your reading guide. The board's like, we haven't done anything today. Okay, this dilution equation is one that you maybe saw in your reading guide. Write down some of that word. It's also quite helpful. So where would we normally use where would we use dilution in real life? It doesn't have to be chemistry, in real life. Yeah. Making Kool-Aid. Okay, so maybe Scott, he's amateur, he's not quite sure exactly how much sugar to powder to water should go into the Kool-Aid because you can't read the back of the package, right? He's working on it, guys. Okay. So he makes it too concentrated. So what's he going to do to make it a better, more edible solution? Add water. So it's just the pitcher, maybe the pitcher that he's made is already full. So how would he dilute that? Takes them out and put it where? In a different container. So we have our initial stock of the Kool-Aid that's super, super concentrated. Takes them out, put them into a different container, and then do what? Either add water to the stock or to this one, right? But either way, it's going to become diluted because you're adding water to a specific volume. So let's say he takes half the Kool-Aid out, puts it in another one, and he dilutes it. The first one we call, the original solution we call the stock solution, and that's what I have in the very back. I've got like 16, 17, 18 molar acid, which is really, really concentrated. So we have this stock solution that we keep in the stock room. That's why it's called the stock. And then we dilute it with water to make it more, eco-friendly, to make it less harmful, to use microscale experiments, and to keep it cheaper because sometimes the huge acid container is very expensive. So the way we dilute is instead of saying, okay, we're going to pour some of this in here, we actually put a number to it. So we'll say the stock solution is generally going to be referring to molarity 1, so big M is molarity 1. The volume of it is sometimes what we're questioning. We're like, how much of the stocks do we need to make another solution? So a lot of times V1 is our question. And that's in accordance with us being given a new molarity and a new volume that we need to make. So anytime you're using these volumes, as long as they're in the same units, we're good. It doesn't have to be liters. It doesn't have to be milliliters. It can be either one. So in this question here, how many milliliters of stock? So what is this looking for? What variable? V1, okay. So V1 is our question. Of a stock solution of 2 molar magnesium sulfate, would you need to prepare 100 milliliters of 0.4 molar magnesium sulfate? So if these two are given together, right? They're given together, they're going to represent the twos in this case, or the ones, but I'm going to stick with the twos. So this right here is V1. I'm sorry, V2. This right here is M2. So what is this? M1. So then the question is, what's V1? So whenever we set this up, information, I've already got them labeled here, here, and here. You can also set them up and label them, just like we did in our gas laws where you took everything down the side of your paper. But I want to solve for V1 in the formula first, and then we'll plug in. So M1, V1 equals M2, V2. What am I going to do to isolate V1? Divide by M1, right? So M1, M1, and so that cancels over here. So then V1 is equal to M2, V2 over M1. What was M2, Trinity? Molar. Just molar, yeah. And you're right to say it is molarity, but we see the M, we just call it molar. So 0.400 molar. What's V2, Jasmine? 100 milliliters. So 100 milliliters. Okay. And then what's M1, James? 2 molar. Okay. So what units cancel? Everybody, what units cancel? Molar, leaving us with milliliters, which is great because that's just a unit of volume. Sorry, molar leaves us with milliliters. So V1 is how many milliliters? What is it? 20, thanks. 20.0 milliliters. So this equation is really easy to use, very easy to use. And so, but what does this number mean? Here's where the part where anytime it asks for you to describe or to discuss how to prepare the solution, this is the part where you have to think about what this means. What does this volume refer to? What is that? 20. Okay, so we're going to take 20 milliliters of stock solution. And how are we going to dilute it? What's the new volume we want to make of the diluted solution? How much? We want to make 100 milliliters. So what do I do to this 20? You add 80, right? But I don't necessarily have to quantify how much water to add. I'm just going to say, take 20 milliliters of stock solution and put in to a volumetric flask. And that volumetric flask looks like, as we show you, it's got a funny looking shape to it. So this is a little big one. Looks like this. So the plots we normally deal with have like a triangle appearance. This one is very specific. There's an etched line in it that is like super accurate stuff. This is a 25 milliliter one. We have hundreds, we have 250, we have 500, we have liters, we have 2 liters. I have tons of these in all different sizes. But that etched line, notice there's no graduation whatsoever on here. So that little etched line right there, you can barely see it. That is very accurate. So what I will say is, we'll add it to a wet volumetric flask. What's the volume of this volumetric flask that we need in this one? I need 100, right? So put into a volumetric flask and fill with water until 100 milliliter mark. So it's just like the etched line on the flask. Yeah.
Make that more accurate.
It's just very well calibrated, and they make them with special equipment. And so those little guys they're much more expensive than normal flasks because it takes so much more effort to make them. So like actually the smaller ones are even more accurate. So I've got some Barbie ones over here. Our Barbie and Ken. These are the little bitty ones. This is a 5 milliliter one. This is a 10 milliliter one. So the smaller they get, the more accurate they get as well. So they're very precise. So let's stick this back here. I also have a beaker. Hold on. This is my little beaker. You see the one on the inside?
Oh, yeah.
This one. So, and then I have a beaker. Okay. So that's just how the description works out. Okay, so how about you guys try this one? Oh, hold on, before I tell you that. Here's what the volumetric flask looks like again. All you do is you take a volumetric pipette, which is a pipette that has a very specific volume. You take it out of the stock, you transfer it over to the other volumetric flask. You fill it to the mark with usually DI water. DI is DI minus water. And if this is a volume to volume preparation, because this was a volume and this is a new volume. So volume to volume prep uses all liquids. Sometimes you'll actually use. You guys see the little powder in the bottom down here? Mm-hmm. You'll put powder. This is what you guys are going to do in your lab today. You're going to put powder of a specific mass into your volumetric flask. And you always put the powder in first, because if you put the water in first, what's going to happen to the powder when you put it in? It's going to stick like crazy to the side of the flask, okay? So put your powder in first, put your liquid in on top, swirl first to get it all really well dissolved, and then continue to fill it up to the etch line, because if you don't swirl it before you get there, there's no space to actually mix it in here. So it's nice to mix it first and then go ahead. So that's what you guys will do. But before you do that, go ahead and solve this one. Measure from the bottom of the meniscus, and that's going to be in line with the etch mark. So it'll look like this. And the etch marks go like right there. Lindsay, come up here and do this one. And then everybody else, after you finish solving that, get out the paper for I'm sure you don't want it. Tell us not to do so. Yeah. Yep. Him is a little off. You can tell. Yeah. Guys, loving it. Morgan, what did you get your answer? Awesome. Okay, so we got 2 confirmations. Who can explain to me how to prepare this solution then? Follow the same standard kind of sentence structure that I used earlier. Okay. Until the 250 mark. So the 250 would be our final volume there. Okay, so this lab is called Mixing Solutions to a Specific Molarity. But there's a couple of versions of this lab that are in your notebook. So I did put a new one up there on your lab stations already. Now, the ones on your lab station say 50 milliliters, but we're going to be making 4 different solutions. So I cut down the volume of the volumetric flask from 50 milliliters to 25. So please put at the top of your paper, total solution, 20, or volumetric flask, 25 milliliters. Whatever it says there, you need to change. Anytime it says 50 milliliters, I want it to be 25 milliliters. So just note that, because at the very beginning of the lab, it's going to say procedure. Before beginning, do the calculations below and have your answers checked by me to make sure that they're correct. Meaning I need to make sure that you're good, that's only 25 milliliters. You're going to be making 4 different solutions of different molarities, and you're going to color code them as green, blue, yellow, and red according to how it says in the lab sheet. Just make sure that you're measuring, you're recording, solution 1 is yellow, solution 2 is green, and so forth. In the lab procedure, it says to check the conductivity of these solutions. So what you're going to have to do to actually do that is you're going to use this probe, and the probes I'll actually connect to these 4 desktop computers. I do have a couple of LabQuest, which are like little handheld data collection devices, and I'll put them at the middle stations. They're just not charging very well, so I don't know how long they'll last. So all you do is you put the probe. You're just going to pour your solution into a beaker, because the beaker is wide enough on the mouth of it to put the probe into it. Because the little volumetric flask is really, really tiny, it won't let you put the probe in. So we'll put the probe in here, and you just dip it in there and swirl for about 20 seconds. And after you swirl for 20 seconds, take the recording of the conductivity. And so that's going to be measured in microsiemens per centimeter cubed. The temperature, you will not be using temperature probes. I want you to feel it, and at the end, you're going to be able to tell me if it's endo or if it's exothermic in terms of the process of making that solution. Just feel it, and I think that'll work. I will definitely ask you to start on the most concentrated ones. It takes a long time for it to dissolve. Okay? So after you get back there and read a little bit, let's ask questions. But right now, same group as last time for the fusion of ice lab. And just your oils and your fingers start to prepare. You will not get shocked. Oh, are you doing that?
All right.